Welcome class to your last lecture set. We are diving into map overlay and geoprocessing, which is a very powerful set of tools that we can use for spatial analysis. This is all part of Chapter 10 and Lab 11. So what is a map overlay? Back in the beginning of this course, I talked about the power of having layers draped on top of each other. That way we can do spatial analysis. With overlays, we have additional tools to help us answer questions. In fact, there are a lot of different geoprocessing tools to help us answer spatial analysis related questions. We might want to know what land use is on top of each soil type, what roads are within each counties. And as you see, instead of dealing with existing length and area data, we get to calculate either automatically with a geodatabase, or we have to do it manually in a shapefile, new lengths and areas due to the kind of geoprocessing that we do. So doing spatial analysis reminds me of one of the first examples that is similar to what ArcGIS and other GIS programs do when it comes to spatial analysis. Back in 1854, there was a terrible cholera outbreak in London. And so Dr. John Snow started to map out the areas that had the most cholera incidences, and also he hypothesized that the water pumps may be to blame. He found a strong correlation between these water pumps and cholera. Therefore, he realized that these water pumps were polluted, making basically everyone around it very, very sick. So he put point data on top of other data that had cholera information to help you analyze what is going on and answer some basic questions like, why are people getting sick from cholera? Map overlay combines both spatial and attribute data. So we get different attribute data and different spatial data based off of what kind of map overlay process that we use. So again, we either combine them in a certain way or we extract certain things out of another layer. You'll see what the options are soon. New data are being created, whether it's just attribute, features, or both. Because we are manipulating data, we must remember the coordinate systems that we are dealing with. Geoprocessing usually involves areas and lengths, so keeping that in mind, you probably should make sure you have a coordinate system that preserves distance and area. Also, understand your coordinate system, or I should say the data frame's coordinate system, and making sure that each of your data sets are the coordinate system that you want and not just the data frame. This is something that we also talked about in the last lecture. We must always be aware of what kind of coordinate systems we're dealing with. If we have geographic coordinate systems and then we use a projected coordinate system in the same geoprocessing tool, we might get erroneous results. You'll talk a little bit more about this, or you'll see a little bit more about this in Chapter 11 when you deal with that in GIS 33. Okay, so going back to spatial joins, remember, if we are, let's say, joining land use parcels with roads, and we want to know the length of a road within each parcel, if you just do a spatial join, it'll join those road records to the parcels, but the length will be the entire length of the road and not just the length within each parcel. For example, let's say this is the parcel that I'm curious about, and I want to join the road to it to see how long is that road, how many miles or how many kilometers is that road within the parcel. However, it's going to give me the entire road length, not just within that parcel. That's where geoprocessing comes into play. Map overlays split these features. So when we are, let's say we're doing an intersect, which we'll talk about in a little bit. When we intersect rows with these land parcels, it cuts each road based off the boundaries of land parcels. Now we can get the total length just within each parcel. It's very powerful. Here's another example. Instead of doing intersect, let's say we're doing clip. With clip, we need a boundary, whether it's a circle like you see over here, a square, or just some other polygon, and we're going to use that to clip or extract data out of the input. So in this case, we are not combining both the input and output data, or I should say the two input data sets to include in the output. The only thing that we'll call this the second data set does is it defines the area for the clip. So like if you have an input here that includes, I don't know, let's say it's both polygons and points, then you would just have the polygons and points within that clip feature. And there's some other examples here with lines and points. So clipping is very common when we're dealing with raster data as well. Erase is something I don't ever do, but people have. It's essentially the opposite of clip. Instead of using a second data set, a polygon, to decide what the data, what the boundaries of the data, it will just remove the data within that boundary. So we just call that an erase. And like I said before, length and area changes are possible now, updated, because it splits features. Very important, if you have a geodatabase, it does this automatically. It automatically updates the length and area. If you have a shapefile, it does not. You have to go in there and calculate it yourself. Also, if you have a secondary length field, let's say your geodatabase feature class is projected with meters, okay? So the shape length and the shape area will be in meters and meters squared respectively. But let's say you have another field called miles. It's not going to update that. You have to do that manually. And this is how you do it. So you go into the table, you highlight that field that you want calculated, and you go down to calculate geometry. You decide what property you want. If it's a polygon, you want area. If it's a line, then you want length. You get to decide what coordinate system you use, either the one that comes with the data or the one that comes from the data frame. I'd be very careful though. I usually use the one that's just comes from the data source. And your unit. Let's say you want acres. If you're dealing with length, let's say you want miles instead of kilometers. Here is another intersect example. So we have residential areas on top, Opechee Formation on the bottom, which is actually pretty harmful. So we're looking at radon infiltration. So we want to know what residential areas are at risk of this radon exposure. So what an intersect does is when you combine these two features together, the output is the areas that both of them basically exist at the same time. It's kind of like using AND with queries. You have to have both the residential and the Opechee Formation simultaneously in the same area. With union, however, you actually add all of it together. Everything comes with it. So if you have geology in one layer and slope class in another layer, then you get a whole set of different polygons that will include data from geology and the slope class. This is like using OR when we're dealing with queries. So this is the output. Here's something that's interesting. Again, with geology, let's say you have all these fields. Slope class. This is basically, whether you have a high, medium, or low slope. With a union, and you click on the new product, you get all of the features. Everything comes together. Now with different geometries come different options, points and polygons. When you're doing an intersect with this, the output dimension must be less than or same as the lowest input dimension. You cannot get data from points and polygons and have polygons as the output. Whatever the lowest one is will be the dimension of the output. For example, let's say we have schools and we want to know what the land use type is at each school. So we're going to do an intersect, and what is the dimensions of that output? It's going to be points. So we're basically going to have land use information, for example right here, low density residential, for each school point. So here's a summary. Erase and clip basically are just used to determine what the output geometry or the output look of the spatial arrangement of the features will be. Clip basically keeps everything inside, and erase keeps everything outside. Intersect only has an output that satisfies both or all of the input features. So again, it's like an AND when we're dealing with a query, but a union outputs everything that is inputted in there. So that's why you see this looking a little bit different, because this shows you that only the stuff inside that circle is going to be kept. However, union over here, everything within the larger polygon, because everything's kept, is the product or the output. Now there are probably dozens of other analysis tools, and you can find these analyses in ARC Toolbox. So we're just going to talk about some other common ones, other information you need to know when you're doing geoprocessing, and then something that we will talk about more in GIS 33, which is Model Builder. We can also do a dissolve, buffer, append, and merge. Dissolve basically has features that have the exact same attribute value for a specific field. They are dissolved into larger polygons. So, or lines, I should say. For example, we have Main Street. For some reason, there are 4 separate Main Street lines. That's redundant. So we can dissolve and we have only one. Down here, we're looking at the state of Iowa. Maybe these are counties, I'm not quite sure. But let's just say that all of these are basically the same. All of these in this color are the same, and all of these in this color are the same, etc. So the dissolve will basically make your data much more concise, and actually could save space because you have less features. This might be another reason why you want to dissolve. You have over here the same parcel with the same attribute data next to each other. So there's really no reason to have these lines. So you might want to do this again because you want to summarize other attributes. And this will probably be the product of your summarization or dissolve. Buffers. Buffers are really important for dealing with proximity. Perhaps you want to know the areas that are 1 mile away from a road. And so you can create these buffers around roads. You can create buffers around points. Another example. I used to work for Southern California Edison, and part of my job as a meteorologist there was I was part of the San Onofre nuclear power plant emergency response team. And we created maps of areas that would need to be evacuated in case there was a nuclear disaster there. And so we created these circular buffers around areas that were going to be most affected, moderately affected, and least affected. And we could do that in GIS with these buffering tools. One thing you have to keep in mind when you're dealing with a buffer is if you want to dissolve those buffers or not. And if you want multiple buffers. You have a lot of options with buffering. Append. Okay, so the next two are called append and merge, and there is a subtle but important difference. Append takes data from the input and adds it to the output, but the output is just one of the layers. It's not a brand new layer. Okay, so it adds features from multiple data sources to an existing data set. Now with certain versions of ArcGIS, there can be some bugs with this, so you might want to look at the help before doing this. Merge actually takes two layers, combines them, and then outputs it into a different data set, into a single new data set. That's the important distinction. When you are combining different data sets like this, sometimes because of subtle differences in the boundaries, you might get a thing called slivers, which are these tiny polygons that don't really mean anything. They're very small. You may not see them until you zoom in, and they're kind of they're a nuisance. It's annoying to have this, but there are some things you can do to prevent or to reduce the number of slivers. You can first try to figure out what common boundaries exist. And if these boundaries of different data layers were digitized using different scales, they may not be right on top of each other. So when you do an intersect or a clip or whatever, you might have slight differences in those boundaries that can cause slivers. You can go in when you edit it, something you'll learn in 33, and remove those slivers. You can also use a snapping tolerance to reduce those slivers. But you got to be very careful with snapping tolerance. Again, this is something you do in editing. If it's too small, then you're not going to capture many of those slivers. But if you make them too large, then you might actually remove what you thought were slivers, but they're actually useful polygons. So it takes a little bit of practice to really use snapping tolerances to reduce slivers. Something else that comes up when you're dealing with geoprocessing is something called the environmental settings. When you're processing these data, you can, and this is actually a useful, these are useful tools, but it just makes the whole, we'll say, process a little bit more thought-provoking, because you got to think about this a little bit more carefully. If you're doing a lot of geoprocessing, you can create your workspace, and instead of having to choose the folder or the geodatabase that you want all these data to go into, you can just use the workspace command and set that for all of your geoprocessing. You can also set up the output coordinates, the processing extent. I'm just going to use things that I've used before. You can do various cartography processing, geostatistical analysis stuff that you want to do, certain other analyses for rasters. So going forward in your GIS career, you're going to encounter some of these options that will help you when you are geoprocessing. I just kind of wanted to remind you, if you are eventually working, let's say, on a project on your own in a different class, you can get a lot of help with ArcGIS and GIS concepts. That's one really great aspect of Esri's products. Model Builder. We're not going to talk about that in this class, but it's interesting enough, and I have quite a bit of experience with Model Builder. What Model Builder does, in the background we're using Python code. Now don't get worried, you're not going to yet be coding with Python, but it's using Python code to create a sequence of geoprocessing. So if you're going to use the same geoprocessing tools, and let's say there's 5 of them, for 20 or 30 data sets, it would be extremely time consuming and tedious to do all that by hand. So you can create a model which basically allows you to drag and drop various geoprocessing, like make feature layer, intersect, all that stuff. And you can store these processing steps for later and run it repeatedly for different data sets. And you can even share these models with others. So this is exciting stuff, and I used this in my landslide research when I worked at the geologic consulting firm. I had to input for every storm of the season. I had to do storm relative precipitation, seasonal relative precipitation, and there were certain processing steps that I had to take every time to attach them to the geology of the land and to assess landslide risk. Thank you. I hope you learned a little bit about geoprocessing, and hopefully now that this is the last lecture, you have a much more solid understanding of GIS and ArcGIS, and I'll see you guys next time. Thanks.